Good morning. I'd like to talk to you today about synthesis of quick return mechanisms, which are very useful devices that you'll find in all sorts of production machinery, which allow you to get a motion that will be faster in one direction than in another. And to give you a little better idea as to just what I mean by that, I want to show you a model of the end result before we see how we get there. So I'm going to show you the last line in the story before I show you the story. Let me get it set up here, and we'll get the camera on it. See if I have it there. That's not too bad. Let me stick this down here. Now, what we have here is a little 4-bar linkage, which you should be familiar with from your earlier lectures or tapes in ME 2310. And I've labeled them link 1, which is the ground link, link 2, which we'll call the crank, link 3, the coupler, and link 4, the rocker. So that's the simplest and most basic 1 degree of freedom mechanism that you can have. Now I'm going to articulate this by putting a nail in that pivot and holding the nail with the pliers to keep my hand out of the picture. And I'm going to move the crank in its motion. It's stubbing its toe on the fasteners there. And you can see that the crank can make a full revolution. This is a Grashoff 4-bar linkage. If you don't know what a Grashoff linkage is, you ought to go read the text about that. It's very important to understand why the Grashoff criterion predicts that this will, in fact, make a full revolution. Notice that link 4 is oscillating back and forth. That's called the rocker. And I want to stop this in that particular position, which is the extreme position of link 4, and make a mark right there. And now I'm going to move it around to the other extreme position of link 4 and make another mark. And while I'm doing this, make note of something you also should already be aware of, namely that in the extreme positions of link 4, this position and that position, links 2 and 3 are collinear. Notice that they are in on the same straight line. And that, in fact, defines the extreme positions of link 4. Now, notice the motion of link 2 as I move it from this position. We'll call that the far position of link 4 back to the near position of link 4. Now, I think I may need to bring some paper around the other side so that I can make a mark here. Let's slip a piece of paper under there. And I also want to make a little mark right down here. Get that in the right position. That's in an extreme position of link 4. I'm going to make a mark for the position of link 2. And I'm going to move back to the other extreme position of link 4. And I'm going to make another mark right there. Now, this does not have a very extreme quick return action, but what I want to demonstrate here is that this angle of crank rotation, which I'll call beta, is not 180 degrees. And if it isn't 180 degrees, then its supplement over here can't be 180 degrees. And in fact, alpha is less than beta. And that's what makes this a quick return mechanism. You see, when link 4 moves from one extreme of its position, of its possible positions, to its other extreme, the far to the near, link 2, which is the driver, perhaps being turned by a motor in a real case, does not go through the same angle. And if I'm driving link 2 with a motor, which is running at constant speed, then running it through a larger angle takes longer time. So if I rotate link 2 in the direction that I'm now rotating it, namely clockwise, then it takes longer to get from the near position of link 4 to the far position than it takes to get from the far position back to the near position, simply because link 2 is going through a smaller angle on the return trip. And that's where the linkage gets its name, quick return. It does a quicker return from its far position to its near than it takes to get over there. Now, all kinds of applications for this exist in machinery, as I mentioned, such as moving a part from one workstation to the next, during which time you are not doing any work on the part, therefore you would like to get it there as fast as possible, and then perhaps moving the part in the other direction under a controlled condition so that you get an appropriate velocity profile or some such. So you quite often want to do work on the part as it moves from one position to the other and just get it back. Perhaps the carrier is empty by that time. You may have dropped the part and you want to get back and pick up another as fast as possible. Now, as you can see, there isn't a very extreme ratio of quick return here, and the kind of linkage that I'm showing you is somewhat limited in that respect. I'm going to show you two types of linkages here that will give you a quick return, one of which is a little bit simpler but has some limitations, and the other one is more complicated but does offer some advantages in terms of its ability to give you larger time ratios. So the first one I want to describe is this Grashoff 4-bar quick return mechanism, which is the one I was just demonstrating to you. That will have a time ratio, which we'll call Q, which can be defined as the time it takes to go forward, and by forward I mean motion of link 4, let's say arbitrarily to the right, we'll call forward, and call this back. And if I describe that Q as the ratio of the time it takes to go forward over the time it takes to come back, and also state that the omega of the crank is a constant, K, then I can equate that time ratio to the ratio of angle through which the crank will go. And those are the angles that I previously labeled beta and alpha. So the time ratio then is simply beta divided by alpha. Now, usually the way you approach these problems is to decide on a particular time ratio that you would like to have. Perhaps it's 1 1/4 to 1, or 1 1/2 to 1, or 1 1/8 to 1. And having decided upon the value of Q, then you need to be able to determine beta and alpha suitable to that value of Q. And that's a very simple procedure, since it's obvious that the sum of beta and alpha must be 360 degrees, since they together comprise one rotation of the crank. And also, since from the definition of the time ratio, beta divided by alpha is the value of Q that you would like to have, and that's your choice, you can solve those two equations simultaneously, and you're going to have a value of beta and a value of alpha, which is appropriate to your particular case. Now, the advantages of this particular approach, namely the 4-bar Grashoff quick return mechanism, are that it's simple. There are only 4 links. It's relatively compact, but it has one distinct disadvantage. Only small time ratios are going to be possible without running into some fairly severe geometric limitations of bad transmission angles and rough running. So a reasonable rule of thumb is that you'll have to keep your time ratio less than 1 1/2, and that may not suit your purposes. But if that is acceptable to you, then it's a reasonable design approach. So what I'm now going to do is show you how to synthesize a Grashoff 4-bar linkage for a particular time ratio. And the time ratio that I'm going to use as an example will be rather small, 1.18 to 1. I'll make a note of that up here, 1.18 to 1. And rather than take the time right now, I've already calculated that that's going to give me a nice even angle, which I'll have available on a triangle, so it'll make it easy to construct. Now, in order to do this particular construction, I'm going to have to define still another angle, which is going to be strictly for the purposes of construction. It's neither beta nor alpha. Let's give it another name. Let's call it the angle phi. And the angle phi is going to be not part of our linkage, but it'll be just a means of constructing some geometry for the linkage. And phi is going to be defined as, by this expression right here. Q is our time ratio, and that's, as I said, 1.18 in this particular case. And this relationship will allow me to determine the angle phi. Very simple relationship. So if I substitute in my 1.18 for this, I'll leave it to you and your calculator to satisfy yourself that my answer is correct, but phi should turn out to be 30 degrees, which is convenient if I'm going to use a triangle to do the construction here. But you appreciate that you could choose any value of q that you wanted up to the reasonable rule of thumb of 1.5 and get the appropriate angle of construction here. Now, having determined this value, let me show you how to go about constructing the linkage with that particular ratio. Now, where do you start in a design problem? That's always the most difficult decision to make. You don't have enough information in any typical real-life design problem, so you have to make some assumptions. And you usually will know enough about your desires or the problem at hand that you can make a reasonable stab at a start to the problem. And what I'm going to suggest here is that we invent a situation in which, for one reason or another, we've decided that we would like the output end of our linkage to move through an angle of 30 degrees, let's say. Again, I'll pick that because I have the triangle available, but it could be anything you like. Now, I have to pick a pivot, and I'm going to pick a point right there on my sheet. And having done this in advance, I'm going down to the lower corner to make sure I stay on the paper, but you could literally choose it anywhere. And if your paper was big enough, you wouldn't have any problem finding the proper locations of all of the other things. Now, since I said I wanted 30 degrees of motion, let me show a little pin there. This is going to be a pivot for my output link. And notice another thing here, which is fairly common in designing linkages, in that I'm starting at the output end and working backwards. This happens largely because you tend to know more about what you want the output end to do than you do the input end, since that's the business end that's going to do the work for you, and you would like to have it end up being something suitable to your machine's needs. I'm now setting my compass to a particular radius, which I'm choosing arbitrarily. But again, this radius, which is going to define the length of link 4, I've just drawn link 4 here. I'll darken that arc in because the pencil doesn't show up too well here. And I'll have to give these some labels here. Let's call this point B1 and call this point B2. It's the same point in two different positions of the link. And I'm going to add some meat to that link so it will look a little more realistic. So this perhaps would be a hunk of metal with holes drilled at either end, and it is link 4. Now, up to now, everything I've done is entirely arbitrary. I've chosen the angle 30 degrees through which the output link is going to move because that's what I wanted. And I've chosen the length of link 4, this distance from B1 to, we'll have to give this a name down here, call this O4, the pivot of link 4. And I've given those dimensions here quite arbitrarily, but your machine packaging would dictate in the real world just what those should be. Now, having made that much of a stab at my design, at least I show the output end, and this being my rocker, I want to force it to go from B1 to B2 and back to B1 and so forth forever and ever. However, since we're after a quick return, which direction I call return and which I call forward is quite arbitrary as well. Let's say that that's the return and that's the forward. So I wanted to come back quick and move forward slowly, back quick, move forward slowly, and so on. That's the ultimate aim. And the ratio, I've decided I want to be 1.18 to 1. So it's going to take 1.18 times as long to go forward as it takes to come back. That's what that means. The next step is to utilize the angle that we just calculated, and I'll refresh your memory as to what that was if I can find it here. I don't see where I put it very quickly, but that was the calculation I did for the angle called phi, which I called phi, which is equal to 30 degrees in my particular case. Well, I think it's under here. I didn't move it. There it is right there. Can you see that? This came out of the time ratio of 1.18 to 1, substituted into this formula and solved. There's only one variable in there, phi, and it's 30 degrees. Okay, back to our diagram. Now what I'm going to do is also quite arbitrary. I'm going to draw a line, any old line, and theoretically you could make this work by literally drawing any line. But some will work better than others, and I'll take advantage of a little experience here and make it go off to the left, which is as much because I have paper available there as anything else. That line now is a construction line. It isn't really part of our linkage, at least not yet. And I've chosen it at a relatively arbitrary angle. It's not too far from 90 degrees to this position of the link, but that isn't required. It doesn't have to be a right angle. The angle phi is now going to be used to draw a second line, which is going to pass through B1, which is the same point in the other position, which second line passing through B1 will subtend the angle phi with respect to the arbitrary line that I just drew. So that means that I need to construct a line at not 30 degrees. I just noticed that I read the wrong number. I beg your pardon. That is 15 degrees. If those of you who were quick enough with your calculator between the time I showed you this and this point have caught me and know that this angle phi for 1.18 ought to be 15 degrees, not 30 degrees. Sorry about that, but we're on the right track now. With a 15-degree construction angle and a 30-degree triangle, I have a little bit of a problem here. But what I can do is draw a line that is at 45 degrees to this line right here. I also happen to own a 45-degree triangle, so that's fairly convenient. And I'll draw a 45-degree line down here, and I'll use that as a base, as a reference, to lay my 30-degree triangle on. Notice down here I'm just going to use that as if it were a straight edge. And I'm going to put my 30-degree triangle along that line and move it along until the other side, the 30-degree edge of the triangle, it goes through B1. And since 45 minus 30 is 15, then this angle right in here is 15 degrees, which is my phi. Now, phi is not an angle that's going to appear on our linkage. It's strictly a construction aid. And I used that angle phi, which came out of the calculation of that formula, to find this intersection right here, which is going to be the pivot for link 2. So I'll label that O2. Okay? Now, that pivot O2 is where link 2, the crank, is going to pivot to ground. And how did I find it? I simply drew an arbitrary line through here and another arbitrary line, not really arbitrary this time, but a line at 15 degrees to the first arbitrary line through B1. Where they intersect is point O2. The next step is to find how long the crank should be. Well, remember the demonstration at the beginning of this tape, which I'll redo right now very quickly to refresh your memory, which said that when link 4 is in its extreme position, 2 and 3 are in line, they're collinear. And when link 4, I should do it this way, I guess. That corresponds more or less to what we've got. And when link 4 is in its other extreme position, 2 and 3 are again collinear. So I can make use of that condition of collinearity now to find a length of crank. And the way I'm going to do that is as follows. I'll take the center O2, which is my crank center, set the compass to B1, to the length O2 B1, strike that off as an arc until it intersects over here on the line O2 B2 extended. Now all I've done is projected the distance O2 B1 around onto the line O2 B2. And the purpose of that is to determine this length right here. We've got to give this a name, I guess. Let's call this C, construction point C up here. The distance B2C, let's write this down over here, B2C is equal to 2 times the crank length. I'll call that R2. It's going to be link 2, and it's the radius of link 2. So if this distance B2C is twice the crank length, then all I have to do is bisect that line. And you should remember how to bisect a line with nothing but a compass and a straight edge, a la Euclid. So we'll just draw a couple of arcs. I'll do this in pencil since we don't really care about the lines other than to find this point right there. And I'll bisect that line. Now I can set my compass to the distance, which is half of B2C. That's going to be my proper crank length. And now I will draw around my crank center O2 that circle, which represents the locus of the end of crank 2. So at least now I have the radius of crank 2. The only thing remaining to be determined, since I have link 4, I have the length of link 2, and I have link 1, do I not? Where is link 1? Link 1 is the ground plane, the paper. And if I have found the location of the pivot O4 and the pivot O2 on the ground plane, then the distance between them, which I will draw in as a dotted line here, is link 1. It is a 4-bar linkage. Often we draw them looking as though they have only 3 bars because the fourth bar is the thing on which we're drawing it, the paper or the ground plane. So I have link 1, I have link 4, I have at least some information about link 2. What remains is to determine link 3. Well, again, we have to make use of the relationship that says that the extreme positions of the output link 4 are determined by the situation in which links 2 and 3 are collinear. That's one arrangement, and flip it 180 and you've got the other. So I can take advantage of that relationship to note that when link 4 is over here at B1, since link 3, being the coupler or connecting rod, connects 4 to 2, and since the locus of 2, the end of 2, is that circle, and we have to be collinear, then that point right there is the connection between link 2 and link 3 for the position shown of link 4 over here. I'm going to draw that in solid. So for the position shown for link 4, here's my link 2 and link 3. There's 3 and there's 2. Okay? And notice that 2 and 3 are collinear when 4 is in its extreme position. Why is that the extreme position? Because that's where I started. I said I wanted 30 degrees of travel on the part of link 4, and I very arbitrarily stuck it there. I could have put it anywhere else. And all of this would have changed as a result. Now, the other extreme position of link 4, which is point B2, will occur when 2 and 3 are again collinear. Well, in order to have my time ratio of 1.8 to 1, and notice here is my alpha, and here is my beta from my time ratio. And alpha, or beta over alpha is the way I had it, is 1.18. And you can check my geometry on that. If I haven't made another mistake, it should be that this, when this angle is 15 degrees, that was our phi. Beta over alpha will be the 1.18. Now, I want to check one thing before I give up on this, and that is that I haven't chosen inappropriate length for link 3. I'll set my compass to link 3's length, and if, in fact, I'm going to have this alpha over beta ratio, then the other position of collinearity, namely there, when link 2 and link 3 are lined up. It's getting rather messy in here with all these lines, and perhaps a little hard to see, but that's one of the problems of laying out linkages. This distance, link 3, since the link doesn't change length, has to be the same here as it is here, and you can see that it is within my graphical accuracy. So, I hope you followed that. The diagram begins to get a little busy toward the end, but I'm going to go back now to our model and show you that we do in fact have something very close to what we started with. I won't guarantee that it's exact, given some of the arbitrary choices that were made. Remember that I drew the line B2C very arbitrarily at the beginning, and I may have done that a little differently than when I made this model, so I expect there'll be a little bit of error. But here we have, I think I have to move this pin. It's getting in its own way. And I'll get my pliers to get my hands out of the way, and we'll move link 2 around in a circle and see that in that extreme position, link 4 is approximately where we have it on the diagram, and in that extreme position, it's approximately in the rightmost position. There is a little error there between my drawing and my model. And we have our Grashoff 4-bar quick return mechanism. Construction method is very simple, very straightforward. It's taken me about 3 times as long to talk my way through it here as it would actually take for you to do it sitting down with a compass and a piece of paper. And I'd like you to try to do that. This same technique is described in your textbook, Shigley, in Chapter 10, so you can look that up if you would like. Now I'm going to move on to a somewhat more complicated, but not tremendously more complicated, but quite more powerful kind of quick return mechanism, namely the 6-bar quick return. And you can figure out what it's going to have by its name. But here are some advantages and disadvantages. This is capable of a large time ratio, even up to 3 to 1, although it may not run quite as smooth at 3 to 1 as it will at 2 to 1. It'll have smooth action despite the large time ratio, and the only disadvantage is that it's more links. And it's only 2 more links, and links are not that expensive to make. All you do is drill a couple of holes in a piece of metal or other material, and you have yourself a link. So that's not a very severe disadvantage. Now, I want to, again, show you the end result before we go through the construction. So let me try and do that, and this is going to be a little harder to do with these models, but we'll see how it works out. For the moment, I'd like you to pretend links 5 and 6 aren't there, and I'll speak to those subsequently. And if we don't have link 5 and 6 yet, we have a 4-bar, which is the same as we just went through. It's a different 4-bar linkage, however. 1, 2, 3, 4. 1 again is the ground plane, 2 is a crank. This is a Grashoff 4-bar. 2 links 1, 2, 3, 4 comprise a Grashoff 4-bar. But it's a different inversion of the Grashoff 4-bar. It's the inversion in which the shortest link is grounded. And I'm not going to tell you what that's called. I want you to think for a minute about what the name of that linkage is, which you should remember from our discussions on Grashoff linkages earlier. I'm going to put a nail in this so that I can turn it, and I'm going to have to hold it up in the air because, well, I won't tell you why. You'll let you figure it out. Again, we're pretending link 5 is not there, but we have a little toe stubbing problem, but we'll get it around. The nail is catching. Maybe I'm better off without the nail. Let me try it with just my fingers. Can you get the camera on that? There we go. Now, I'm moving link. I'm holding on to link 1. That's my ground plane. And the only reason I have the big tail sticking out on link 1 on either side is to give my fingers a place to grab it. As you'll notice, I have to move my hand from one side to the other in order to get the thing to go around completely. Well, do you know what that is called? Actually, I've kind of given it away because it's written right on it. That's a drag link mechanism, and also known as a double crank. It's a Grashoff double crank, the inversion in which the shortest link is grounded. And that has the feature of having two cranks. In this particular case, link 2 is the driving crank and link 4 is the driven crank, but I could just as well reverse that and drive it backwards if I felt like it. But the way I've designed it here, 2 is the input and 4 is the output. Okay? So, that doesn't in itself look like much of a quick return mechanism, and it isn't yet until I add link 5 and 6. So let's now consider their inclusion here. And I'm going to try and pin link 6 down over here on the lower right. That's going to get pinned down to the ground. And you appreciate also that link 1 is pinned down to the ground. So I now have 3 ground pivots. This one, which we'll call O2, this one, which we'll call O4, this one we'll call O6. Let me label them as such. I think that O2 belongs there. That's O2 right there. So we'll call that O2, O4, and O6. Now again, I'm going to have to hold link 1 up in the air because in the drag link mechanism, both of the ground pivots are passed over by the cranks. So I can't just pin the thing down to the drawing board. I'm going to move that over so we can see what's going on here. Now notice that link 6, if I can get my hand out of your way, is rocking back and forth, much like link 4 was on my Grashoff crank rocker. And link 6 is going to be my output link. That's going to be my output rocker, and that's going to have the quick return feature. So if I drive link 2, I'm going to put the motor on link 2, and if I drive link 2 at constant speed, it's a little hard to see here because I'm having difficulty going at constant speed with it stubbing its toe on the cardboard and so on, and having to pass my fingers from one side to the other makes it difficult to demonstrate. A drag link is a very difficult model to build because of the fact that the links all pass over the pivots. It's not so difficult to build in metal, where you can make some healthy pivots, but in cardboard it's not too good. But I think that gives you a little idea as to where we're heading. So what I'm going to do now is show you how to synthesize a particular arrangement of 4 bars which will comprise the drag link portion of this. And having done that, that drag link portion being synthesized for a particular time ratio, all we then have to do is tack on link 5 and link 6 in any way we like, and I'll show you how to do that, and we'll end up with a rocking motion, if we so desire, on link 6, which will be analogous to the rocking motion we had on link 4 on the other mechanism, and there will be a quick return. And I'm going to use the example here of 2-to-1 quick return ratio, which is larger than you can achieve with the other method. Now this method's a little bit more complicated, and there's nothing in your textbook on it, so you might want to take some notes, or the best situation would be is if you have a compass and straight edge and some paper with you, you can follow along and do the construction with me. What I'm going to do is set my compass to a very arbitrary length, which is going to represent the radius of link 2. And that can literally be any length that I like. Another feature of linkages in general is that they are linear. I can multiply the lengths of all of the links in any of my linkages by any constant, and I still have the same kinematic linkage. The motions will be exactly the same. The velocities and accelerations, of course, will increase because the dimensions have increased, but the positions will be the same, the angular positions. And therefore I can draw and design a linkage to arbitrary size and later enlarge it or reduce it in effect photographically, and I still have the same linkage. So I just chose a very arbitrary radius, which is going to be the locus of the end of link 2. And let me show you what that is ultimately going to amount to. I have a little link 2 here, which has not been attached to anything yet, and therefore all I've done so far is define that I have a little link that is capable of doing that about that center. Okay? I've also very arbitrarily chosen the location of O2 here, such that it will stay on the paper. Now, the next step is to draw a set of axes through the center O2, mutually perpendicular axes for sake of construction. So I'll do that. Okay, and we will use those now to begin our construction. Now, as with the Grashoff 4-bar, I have to have some knowledge of my values of beta and alpha, which will be the crank angles through which this crank goes to give me a particular time ratio. Now, if I want a time ratio Q of, let's say, 2, then from the relationships beta plus alpha equals 360, and beta over alpha equals Q, I can solve those simultaneously, and you can do this one in your head with a value of 2. You want beta to be twice alpha, and they both have to add to 360, so it sounds like beta must be 240 degrees, and alpha must be 120 degrees. It gives me the 2-to-1 ratio, and they add up to 360. So, with that calculation out of the way, I can now begin to construct this drag link mechanism to give me that time ratio. And what I'm going to do is take the smaller of these two angles, namely alpha, which is 120 degrees, and I'm going to lay that angle out with its apex at the center, O2. And I also am going to, for the sake of symmetry, for no other reason, what I'm about to do is not necessary to the solution, it's just convenient. I'm going to lay that alpha out such that it's symmetrical about one of the quadrants of my axes. And remember that the axes were chosen very arbitrarily, so this bit of symmetry is strictly for convenience. I should also point out at this juncture that there are an infinity of solutions to this problem. So all we have to do is pick one. So what did I just do? I bisected this 90-degree angle with my 45-degree triangle so that I could get a center line. And then I put my 60-degree triangle in there and drew a line 60 degrees from that and did the same over here. So this angle right here is alpha, 120 degrees. And it also is symmetrical about the fourth quadrant there. And if I chose to do it about a different quadrant, all I will do is get a mirror image of the solution. So I now have this line right here, which I'll draw in solid, which is going to represent link 2 in a particular position, namely a position that gives me an extreme position of link 4 that I can use for my quick return. And I'll show the other position dotted down here of link 2 in which I'm interested. Of course, there's an infinity of positions of link 2 because it can rotate about O2 and stop it anywhere you want. So here's link 2. And this angle right here is 120 degrees. All right. So far, we've defined only one link. So we haven't really gone very far in our solution yet. The next step is to define another link length. And it may seem somewhat odd to you that this next step can be done quite arbitrarily. And I'm cheating because I've already solved the problem and I'm picking a length that will match my cardboard model. But you can literally pick any length for link 3, and the length that I've chosen is what the compass is set to, such that you are able to cross this axis, and let's give the axis a name. Let's call it sigma to sigma prime or something like that. I guess I got a prime on both ends, make a double prime over there. So I've got a sigma prime over there and a sigma double prime over there, just to give the line a name. And what I want to do now is find a length of link which, when attached to link 2, right there, will in one position intersect this line way over here, and in the other position, which is the magic angle of 120 degrees, also intersect. Now clearly there are some lengths that will not meet that criterion, right? If I have it too short, it isn't going to make it. That is, this length will make it over here. I can intersect it over there, but I can't intersect it over here. So all I have to do is have it long enough. Not a very severe constraint. And I did originally pick that length very arbitrarily when I laid it out. I'm copying what I did before simply to match the model that I've made so that I can show you what this looks like when we're done. I'll draw this link in now. This is link 3. And over here where the other arc intersected, I will draw in link 3 in its other position, which I'll draw dotted. It also developed a slight bow going from here to there, but we won't worry about that. So I have now defined two links, link 2 and link 3, and I have them shown in two positions. This is also link 2. O2 is that little center right in there. Two links to go, 4 and 1. Well, what I probably haven't made clear in terms of where we're headed is that the construction here, which, contrary to what I did before on the other linkage, is starting from the input end of the linkage and working toward the output, is nevertheless directed toward having the output link be in two extreme positions, both of which lie along line sigma, sigma prime. Therefore, link 4 wants to be lying along this line when 2 and 3 are as shown here, and also be flipped 180 degrees and lying along the same line when 2 and 3 are over here. Because if link 4 goes through 180 degrees when link 2 goes through 120, then it will also go through another 180. 4 will go through another 180 when 2 goes through the next 240. It has to, because there's only 360 for link 4 to go through. So that's where I get my time ratio. When link 2 goes through 120, 4 is going to flip through 180. When link 2 goes through the next 240, link 4 is going to flip a second 180. And that's my time ratio. So all that remains now is to find where to stick 04. Where does the pivot 04 go? Well, link 4, by definition, connects link 1 to link 3, at least by my numbering system. And therefore, this position, this little pin over here, which I'm going to call pivot 3, 4, which connects 3 to 4, is the same as this connection in a different position, 3, 4 over here. So if I have the constraint that link 4 must, for both of the positions shown, lie along the line sigma, sigma prime, and also connect to pin 3, 4, then I think it follows, I know it follows, but I hope you agree with me, that if I bisect that line 3, 4 to 3, 4, which I'm doing by the same Euclidean technique as I used before, we'll just drop a perpendicular there and find that intersection, which is the bisector of this line right here. That is the pivot 04. This is the pivot 02, where we started. And here again the drawing begins to get very busy, because these constructions typically are done with two links lying coincident, and therefore everything is on top of one another when you're all done drawing them in. There's link 4. And link 4 on the other end, still pivoted here, has to come over and connect up with 3, 3, 4. Sorry, 3, 4. Again, the linkage is being constructed in a triangular configuration such that there is an extremum present. The extremum is defined by the collinearity of link 1, which is the line sigma, sigma prime, and the link 4. Those are collinear in this case. Now that, I hope, will be a little more clear when I put some physical links on here. Here's where we started. Defined a link 2. Totally arbitrarily. I just picked a length, what I felt like at the time. I drew the locus of the end of that link 2 as it would pivot about this center. That center was also chosen arbitrarily. The line sigma, sigma, sigma prime, sigma double prime, as I've labeled it, was also drawn arbitrarily. The angle, which is not arbitrary, which is a function of our desired time ratio of 2 in this case, was laid out symmetrical about 1 quadrant. The symmetry is arbitrary. It will work even if you don't do that. You might not get quite as nice running a linkage, but that's another issue. Link 3, its length was determined quite arbitrarily, and such that it intersected the line sigma, sigma prime. Once I've made those arbitrary choices, I have now narrowed the problem down to a single solution. Remember, we had an infinity of potential solutions at the beginning. The next step I did was to bisect the line from position labeled 3, 4 over here, 3, 4 over here, to find this pivot right here, which then defines the length of link 4 and simultaneously defines the length of link 1. And again, they're laying on top of one another, so they've kind of disrupted themselves. But let me move now to the model which I started with and show you that that does in fact accomplish what we're after. Here's where we are right now. Link 2's length has been defined. Link 3, link 4, which is almost completely hidden under here until I move it. Now I will rotate the whole mess and notice that, again, we're temporarily ignoring link 4, I mean link 5. Notice that link 4 ends up having gone through a 180-degree flip, but link 2 has only gone through 120. Now when I rotate link 4 around to where I started from, link 2 goes through the remainder, which is 240. There's my 2-to-1 time ratio. So now I have my drag link, and I'm going to move it up there so that it looks a little prettier. At least you can see the links. The final step is very simple. All I need now do to get link 5 and link 6 is much the same as when I started with the design of the Grashoff 4-bar. Namely, I choose an angle through which I would like link 6 to travel. And I define that angle. Let me sketch that in. Let's say that I pick a pivot for link 6 down here, and I define an angle quite arbitrarily. I'll just sketch it freehand here, through which I would like link 6 to go. Call it theta 6. And that's anything I feel like. Once I have defined that, and notice that I put the other end of link 6, here's link 6 right here in one position. And it's going to move over to here. The other end of link 6 is deliberately placed on the line sigma prime to sigma double prime. That's a requirement, because I want link 5 to drive link 6 to that position. I don't have it in the same place that my cardboard is going to put it. Let's correct that. There. There's the pivot I want right there. So that when link 4 is lying along sigma, sigma prime, link 6 is all the way to the right as far as it can go. Why? Because 5 and 4 are collinear. Then when I continue to move link 2 around through 120 degrees, link 6 comes all the way back to its leftmost position through whatever angle I chose. And if I don't like the angle, all I have to do is move this pivot down or up to change the angle. The total excursion of link 6 is going to be completely defined by one thing, and that is this radius right here, this distance. Notice where link 5 is coupled to link 4? That distance right there is half of the distance that I wish link 6 to move. So all I have to do is choose an excursion of link 6 that I would like, decide on an angle. That determines the pivot. Once I've chosen the excursion, I will cut that excursion in half. Let me move this out of the way. This is the excursion of link 6 I'm talking about, right here. Call it S6. And if I do the same bisect trick with my compass and cut that distance in half, and I take that radius which is half of S6, and I find where that lives on link 4, right there, and I drill a hole in link 4, which is this hole right here, and I attach link 5. Presto. I now have a 6-bar linkage which drives link 6 as the output, link 2 is the input. I stick my motor on link 2, I drive link 2 at constant velocity, one direction or the other. It drags link 4 along for the ride, thus the name drag link mechanism. Link 4 in turn drives link 5. Link 5 makes link 6 oscillate, and I have a 2-to-1 quick return. Now you can also have your output on link 6 be a slider block. For example, I could, if I wished, have link 6 constrained to move in a track, in a straight line, which I'll do with some pins here. Need one more pin. And now, instead of a rotary motion on the part of link 6, I have a translating motion on the part of link 6. Again, I'm having trouble holding everything together here because I can't pin link 1 down. I just pulled it out of my track, I guess. I can't pin down that link 1 because the pivots have to pass over it. My hands are getting in the way of everything as well. I hope you get the idea of what's going on there. So the actual motion of link 6 is quite arbitrarily defined. It's whatever you would like it to be. The quick return ratio comes completely from the geometry of the drag link, and it really is a simple exercise to lay that out to get any time ratio you like. So to summarize what I have shown you, I've shown you 2 techniques to synthesize quick return mechanisms, one of which uses only 4 bars, but has the limitation of very small time ratios. Actually, anything above about 1 1/3 begins to become problematical, and 1 1/2 to 1 is about the largest that you can possibly consider. The second is the one that we just went through, which is the 6-bar quick return. It's a little bit more complicated, a little harder to follow the construction, but really not that difficult, and very simple to make in metal, not in cardboard, and has very many applications in industry. So I think I'd like you to try to make a couple of these, and you'll have a much better idea of what's involved. Thank you.